Section 4-9 is on related rates. The objective of this section is given a problem in which several quantities vary. Predict the rate at which one of them is changing when you know the other rates. And as you probably have noticed in the previous chapters, they usually wait until the last section of the chapter until they really throw a tough section at you, and they did not disappoint in this chapter either. Related rates are definitely not an easy topic. However, if you look at the name of it, it pretty much describes exactly what we're doing. The name of them, these rates are called related rates, and we call them related rates because of the fact that we're going to come up with a relationship between rates. And how do we get rates? Well, we know that a derivative is a rate of change. So we're going to use some sort of a derivative to generate an equation that has multiple rates in it. Thus the term, related rates. So let's take a look at the guidelines that we can use to help us solve these related rate problems. Now again, these are just a series of guidelines here. There's nothing I can tell you that if you set up every single problem a certain way, you'll get the answer for everyone, because it depends on the problem as to how exactly you go about setting it up. But if we follow these guidelines, it will help me set the problem up properly, so it will lead me to the answer that I'm looking for. So the first guideline here is to write the rates that you know, and include units there when appropriate, which basically all these will include the units. So write the rates that you know, and we'll actually write it that way, what we know, and write down those rates. The second thing you want to write down is the rates that you need to find. And again, those are the terms that we're actually going to write down, what we know and what we're trying to find. And that will at least give you a game plan as far as what you know and what you're trying to find will help lead you in the direction that you need to go in order to get your solution. And then once you have those rates that you know and that you are trying to find written down, you can then write an equation that relates the variables in those rates. This is the reason why writing down those rates is extremely important, because the equation that you're going to need to use in order to solve this problem is determined, or is going to show up because of the rates that you've written down. And step 4 of this process is to differentiate implicitly with respect to time, and we use t for time here. So when we talk about implicit differentiation, we just talked about that in the last section. That's where you get those y primes and so forth that show up in your problem. And we're going to get an equation once we take the derivative that has multiple rates in it, thus the term related rates. And then finally, step 5 here is to solve for the rate you need to find. So you're going to have multiple rates in there, and then they're going to tell you some information about some rates that you know. You're going to solve for the one that you're trying to find. And the last step here, although it seems kind of obvious, but answer the question that's asked. Go back and reread the question that they ask you, and make sure you've answered that question. Sometimes it's easy to go through and find this derivative and do all these things, and at the end you just leave your answer and move on, and yet you didn't answer the question that they asked. So make sure you go back and reread the question to make sure you've answered it. And if we follow those guidelines, they'll put us on the right path or the right direction here for us to come up with a solution to this related rate problem. All right, so let's take a look at a few examples here that illustrate some related rate problems for us. So here's the first example. You have a pebble, it's thrown into the water and it causes a circular ripple. That's a big hint there, circular ripple, circular, to spread outward at a rate of 2 feet per second. So that's a rate at which the radius is changing. It says find the rate of change of the area when the radius of the ripple is 6 feet. All right, so again, the first step of this process is to write down what we know and what we're trying to find. So they gave us one rate in here. So we know that one rate. And the one rate that they've specified, I'll underline it up here, but they told us that the circle was increasing at a rate of 2 feet per second. We say the circular ripple is spreading outward, it's increasing at that rate. We're talking about the radius is increasing at that rate. So that's telling you the change in the radius over the change in time. So that would be dr dt. We're going to use r for our radius, and we're going to use t for our time. And so dr dt represents for us the rate of change of the radius. And so they told us this was equal to 2 feet per second. And again, you see the rate there, dr dt. R is measured in feet, and our time t is measured in seconds. That helps us see that those units correspond to the rate that we wrote down. So that's the rate that we know. Let's write down now what we're trying to find. So it says find the rate of change of the area. The rate of change of the area, that would be the change in area over the change in time. So that's dA dt. The change in area, rate of change of area. And we want to find dA dt when the ripple is 6 feet, when the radius of the ripple is 6 feet. So when r is equal to 6 feet. So I know a rate, I know the radius that I'm going to use. I just need to find out what dA dt is equal to. So that's the first 2 steps there, writing down what you know and what you're trying to find. First 2 steps of those guidelines we just went through. The next step of the guidelines were to look at the rates that you wrote down, and in particular look at the variables that you have in there. So I've got r for radius, I've got a for area, and I need a formula or an equation that relates those. That's how I'm going to come up with my related rates, as I create an equation that involves or that relates these 2 variables, and thus a derivative will come up with a related rate. So I know that for a circle, which is what we're talking about here, it says it was a circular ripple. The area of a circle is equal to pi r squared. So there's a relationship between the area and the radius of this circle. Now again, for most of the problems you're going to find they're not going to give you that relationship, just like we have here. You've got to figure that out. There are some where they will give you that relationship. Here's one where you had to figure it out. Now, what I want to do is I want to take the derivative of this equation with respect to time, with respect to t. And by doing so, you'll notice that I'm going to get, when I take the derivative of a, for example, with respect to t, I'm going to get a dA dt to show up. That's the rate I'm trying to find. Over on the right with the r over there, I'm going to take the derivative of that, and I'm going to get a dr dt to show up, which I know. They told us that. So I want to take the derivative with respect to time for my rates to show up. So let's take the derivative. Derivative of a with respect to time is known as dA dt. On the right side, you have a constant pi times a function r squared. So our rule there is the constant stays out front, and we multiply by the derivative of our function. Follow chain rule when I take this derivative. Derivative of r squared is going to be 2 times r to the first power, which I'll just write as 2r, times the derivative of r with respect to time. That's the derivative of the inside function there, dr dt. So it turns out dA dt is equal to pi times 2r times dr dt. Now the next step of this was to, after we take the derivative, and notice we get a relationship between these rates right here when we did that. The next step was to solve for the rate that you're looking for, and we're trying to find dA dt, which our equation is already solved for dA dt. So all I got to do is substitute in the values they told us. If I go back up here, we said dr dt was 2, and we're going to use a radius of 6. So dA dt is equal to pi times 2 times the radius they said was 6 times dr dt, which we found they told us was 2 feet per second. And so this turns out to be 2 times 6 times 2. That's 24 pi. And the units in this, look at your rate. Our rate is the change in area. So area in this problem would be measured in square feet divided by the change in time. And time in this problem is measured in seconds. So it's square feet per second. And those are the units that we end up with there. So 24 pi square feet per second. The change in area with respect to time. There's your first related rate problem. If you need to, go back and watch that again just so you can see how we were able to come up with the relationship between these rates. Let's try another example though. This one says the sides of an equilateral triangle increase at a rate of 2 inches per second. Right there's a rate for us. Find the rate of increase of the area when each side is 50 inches. And they give us a little hint here. This time they tell us a relationship between the area and the sides of this equilateral triangle. Area of an equilateral triangle is equal to root 3 over 4 times s squared. All right. So again, let's start this out the same way. Write down what you know and then what we're trying to find. So I know one rate. They told us in this problem that the sides of an equilateral triangle are increasing at a rate of 2 inches per second. That's the rate they told us. So I know that the change in the side length, ds, over the change in time, dt, is equal to 2 inches per second. Again, the inches per second, your side length is measured in inches, your time is measured in seconds. So that's ds dt. That's what we know. What are we trying to find? They asked us to find the rate of increase, or the rate of change of the area when each side is 50 inches. So we're trying to find the change in area, just like we were doing in the last problem, with respect to time, dA dt. And they said to do that when the side length is 50, when s is equal to 50 inches. All right, so there's our game plan in essence. We know the ds dt, the rate at which the side length is changing, and we're trying to find dA dt, the rate at which the area is changing. So I need a formula then that relates the side length and the area of this equilateral triangle. Well, again, they were very nice in this problem and told us that. They don't always give us that like we saw in the last problem, but in this case they did. They told us that the area is equal to root 3 over 4 times s squared. So that was nice. They gave us that. We want to take the derivative of that formula with respect to time. So let's try this. Take the derivative of the left side. Derivative of a with respect to time is known as dA dt. That's a good thing that that showed up because that's what I'm trying to find. On the right side, again, I have a constant times a function, s squared. So the constant stays out front, root 3 over 4. Derivative of s squared, follow your chain rule. It's 2 times something to the first power, and you substitute in the inside function, that's s. And then you multiply by the derivative of the inside function, that's ds dt, derivative of s with respect to time. Again, when you get done with this, you better have a relationship between rates. That's what we're working on here, related rates. So the fact that I end up with an equation that has a relationship here between two rates, that's good. Of course, you got to make sure your derivative you took was correct. Make sure if you're using composite functions, you use chain rule, products of functions, you're using product rule, etc. And now let's just substitute in what we're looking for. I already have this solved for dA dt, so I don't have to solve for that. Sometimes it's not solved for that. If this problem, for example, it asks us for ds dt, I can see I'd have a little bit of work to solve for that. This one didn't ask us to do that. It asked us to find dA dt. So I've got root 3 over 4 times 2. And the value of s, they said find dA dt when s is equal to 50 right there. And they told us that ds dt was equal to 2 inches per second. Again, having all that written down helps me solve this problem. It also helps me come up with the right equation as well. And so now to simplify this, I guess we have 2 times 2 here. We'll cancel out with a 4 actually, so we end up with 50 root 3. I'll write it just like that and leave it like that, 50 square roots of 3. And the units for this, again, look at the units of our area here. This was measured in inches, so the area, I should say the side length was measured in inches, so the area is going to be in square inches. And our time, the t, is measured in seconds. So this would be square inches per second. Here's our solution to that related rate. And now the last example here for us to look at is the following. It says the width of a rectangle is decreasing at a rate of 1 inch per second, and the length is increasing at a rate of 2 inches per second. They gave us two rates in this problem. It says find the rate of change of the area, there's what we're trying to find, at the moment when both the length and the width are 10 inches. All right, so let's write down again the same thing here, what we know and what we're trying to find. So as far as what we know, actually, oops, I'm going to need a little bit more room here because I've got two rates that I know actually. So let's start with what we know. They gave us two rates. Let me scroll back up here so we can see both those rates. They told us that the width of the rectangle is decreasing at 1 inch per second. I'm going to underline the word decreasing as well. So they told us that the width is changing at a rate of 1 inch per second. It's decreasing at that rate. So that would be the change in width, dW, over the change in time. And that's 1 inch per second. I underlined the decreasing part for this because if they tell us that the rate is decreasing, or excuse me, if they tell us that the width is decreasing, that means the rate has to be negative. Those two go together. Remember, if your function is decreasing when you look at it graphically, that means that the derivative of that function is negative. That's the same thing we're looking at here. The second rate that they told us was that the length is increasing for this one at a rate of 2 inches per second. So we're going to call that dl dt is equal to 2 inches per second. All right, so those are the two rates that we know. And let's write down the rate that we're trying to find. And again, they actually asked us to find the rate at which the area is changing. Find the rate of change of the area. So again, this one's asking us to find dA dt. Now, not all of these are going to ask you to find area. Our examples all asked for area, but they won't necessarily all be asking for area. And they said to do that when the length and width are both 10. So when W is equal to 10 and L is equal to 10. Okay. So again, look at your rates now. I have width, I have length, and I have area for some rectangular region. I need a formula that relates those. Well, I know for the area of a rectangle, the area of a rectangle is equal to the length times the width. So I want to take the derivative of area equals length times width with respect to time. So over on the left side, when I take the derivative, I have the derivative of A with respect to time. That's known as dA dt. Over on the right side, now be careful there, I've got L times W. That's a product of L and W. So if I'm going to find the derivative of a product, I have to use product rule. So product rule says take the derivative of the first function there. Derivative of L with respect to time would be dL dt times the second function, W. Add that to your first function, L, times the derivative of the second function. That's going to be dW dt. It's the derivative of it with respect to time, remember. So you get dW dt. Notice in this problem we end up with three rates. And why do we end up with three rates? Well, because there was three variables in my equation. In the previous problems, there was only two variables, so I ended up with two rates. Here I have three variables, A, L, and W, so I get three rates. But the key is that it's a relationship here between those rates. It's a related rate that we came up with. And now, again, the first step is to solve for the rate you're trying to find, which we're trying to find dA dt again, so I don't need to solve for that. I really just have to substitute in values. So let's substitute in our values here. dL dt, they told us was equal to the 2 inches per second. W, they said, was 10. L, they said, was 10. And then finally, the dw dt was equal to a -1. So you have 2 times 10 is 20, plus 10 times -1, that's a -10. 20 plus a -10, that sounds like 10, is dA dt. And again, put units on this thing. The length and width were both measured in inches, so that means that the area of this thing is going to be in square inches. Again, that's the area. Over the change in time, which the rates at which the length and width were changing were in inches per second, so this is going to be square inches per second then. Turns out that's the same as the radius and or the width and the length on this problem, but they don't always obviously end up being the same. But the rate at which the area is changing is 10 square inches per second. All right, that's as far as we're going to go in this first part of this section.